Lesson 7 will cover Chapter 4 of our textbook, Linear ODEs with constant coefficients. Here is the standard form. Previously, we used to focus upon the second order only, that is, a special case n equals to 2. Here in Lesson 7, let's consider the arbitrary case. N can be any positive integer. Like before, let's simplify the left-hand side by introducing some differential operators. Let's begin with these two, d for the derivative operator and I for the identity operator. And then we can define d to the mth power as the repeated application by composition. So decomposition, and so on, repeated m times. So what do you mean by that? We're just applying d, which means applying the derivative m times. So what do you get? Of course, the mth derivative. And finally, we define d to the 0 power as I. So we are taking the derivative, but 0 times. So we did not take any derivatives, so nothing changed. So that's just the same as the identity. Under this notation, we can re-express this original ODE in the following fashion. Like this. Or equivalently, L of y equals to f, where L is given by this polynomial expression of d. Now, did I say polynomial expression? That polynomial is called the characteristic polynomial, a polynomial given by the coefficient structure of this original ODE, an, an minus 1, an minus 2, and so on, all the way down to a1 and then a0, like this one. That's basically what I'm talking about. The polynomial q of s, given by an s to the nth power plus an minus 1 s to the n minus first power, and so on and so forth. Now, this is equivalent to the latter form down here, which is obtained by replacing d in place of s. Then what did I get? The same as before. So L and Q of D are the same thing. So it is possible to express the same ODE here as L of y equals to f, or Q of D of y equals to f. They all mean the same thing. And I'm going to mix those up so that you're exposed to all these. As a matter of fact, our textbook author does the same thing. Sometimes he uses this one, sometimes like this, L of y equals to f. In some other times, like this, Q of D of y equals to f. They all mean the same thing. But the final expression here has one advantage. Because from here, in the right-hand side, it is possible to factor it in the complex number field. We can apply so-called the fundamental theorem of algebra, which says any complex polynomial can be factored all the way down to the linear factors. And if you want a little bit further explanation about all these, you can go down to lesson 1a, the preliminaries. In short, you're going to get this kind of expression. An, the linear coefficient, times s minus lambda 1 to the m1 power, and so on and so forth. Here, the complex numbers lambda 1, lambda 2, lambda 3, those are the zeros of this characteristic polynomial q of s. And m1, m2, m3, those are the multiplicities. And the multiplicities are positive integers, 1, 2, 3, 4, and so on. But they all have to add up to n, the degree of this polynomial. Now, if I apply that to q of d, then you get the latter expression here. And that can be quite useful down the road. Let me give you a brief preview here, okay? I'm going to do something without proving anything. I'm going to prove those later in sections 3 and 4 later. So if d minus lambda ji to the mj power of y is equal to 0, then q of d of y is equal to 0. That's because if I highlight this jth factor of this operator, then that corresponds to this jth operator here, like this. And that'll make this entire thing 0. The reason? I can always change the order. So that the rest of this y is 0, so apply 0 to the remaining operators, then of course that's 0. Why can I do this? Because we have all those commutativity in all those multiplications. Basically what we are doing is multiplying d times d many times, and that's commutative because left hand side and right hand side is the same. And also d times I or I times d. And the identity is commutative with everything, so yes, everything is commutative. And for detail, well, all those details about commutativity and so on will probably have to be covered in Abstract Algebra 1, Math 3510. So the detail is just left to the students to pick up. We're going to just use these. Now, as for this red operator, d minus lambda ji to the mjth power of y is equal to 0, we have actually these functions, which I'm highlighting in red. So t to the m power times exponential of lambda jt. And m can be 0, 1, 2, 3 all the way over to mj minus 1. It has to be less than the multiplicity. These multiplicities here. Then we can actually prove that this red operator of y is equal to 0, and that's just brute force proof. Okay, it's not exactly brute force. You need to have some recursion, so it can be a little bit tricky. Not too bad, but we can do it and we will do it later. And in the end, what do you get? We get q of d of y is equal to 0. So what do we get? We got some solutions of this homogeneous equation. Q of d of y is equal to 0. The right hand side 0. And then how many did I get? Mj of them. M is running from 0, 1, 2, 3 all the way up to mj. And then there are many factors. M1, M2, M3 all the way to mk. So there are k factors. And they all have to add up to what? N. You see? Multiplicities have to add up to n, the degree of the polynomial. So what did he end up with? We just found n linearly independent solutions of the homogeneous equation. It works like this. Okay, so much for the preview, and if you didn't understand anything, it's fine. We're going to come back and discuss all those with proofs and so on. So let's move on. The next topic here, so-called the fundamental theorem, is something, okay, there are two types of fundamental theorems here. The first one, let's discuss. A linear ODE with constant coefficients has a unique solution under a given initial condition, which means whatever we are doing makes sense. If you develop a theory and later on that thing does not exist, then everything is just going down the drain. So the fundamental theorem is really important. It has to make sense. There is something exists, and then it has to be unique. There's only one of them, so everything makes sense. And how do we prove that? Here is a brief version. Okay, we have an ODE and IC, and then we take the Laplace transform and break apart the left-hand side and apply those input derivative rules. And then simplify and take the like terms together, and you saw this before. We have the characteristic polynomial times y, q times y, minus a polynomial of degree at most n minus 1. So q times y minus r is equal to f. So flip this r of s to the other side and then divide by q of s, and what do you get? R of s over q plus capital F of S over Q, and then you take the Laplace inversion. What do you get? The homogeneous part plus the particular part in general. And then what do you have? You have a solution. So not only did you get the existence uniqueness, yes, you find it, but also we established the method of how to get the solution. That's basically what we had been doing in chapter 2. There's one little problem, however. What if the Laplace transform does not exist? Or the Laplace transforms of y and that of f, they do not exist, and what do we do? That is a potential problem. You see, what if f is not a function of exponential type? Then what? That's actually a bit of a problem. In the end, it turns out okay, but there's a bit of a hole to pick up. But if you want to fill that hole, then you can do it this way, but this is going to be a hard way. I'll just tell you that it works out in the end. Eventually, what do? We solve for nth derivative of t because the leading coefficient cannot be always 0. Otherwise, this is not going to be an nth order. So solve for that. And then we get this kind of expression. And then we do something ingenious. We introduce n functions given by all those derivatives. Original as x0. Derivative is function x1. Second derivative as function x2, and so on. Then you're going to get this system of ODEs. x0 prime is x1 because this is y prime, and that too is y prime. And x1 prime, so y prime prime, so y double prime is y double prime, and so on. And finally, xn minus 1 prime, so that's y to the nth minus first derivative, and then take one more derivative, so that's nth derivative. And the nth derivative is equal to that. So put all those y, y1, y prime, y double prime, all the way those back in. You can rewrite those in terms of x0, x1, and so on and so forth. So in the end, we end up with a matrix expression like this. And eventually, we can simplify into a certain function, a multivariable function of t and the vector x itself. And then we can prove that this function is so-called Lipschitzian with respect to the second variable. Yes. And then we can apply the fundamental theorem of first order differential equation for multivariable case. That's a hard way to do it, but it always works out. Okay, if you didn't understand the thing, that's okay. There's a reason I de-emphasized it in gray. And one day I may cover it in Real Analysis 2 or some higher level course. But for now, let's just stick to the first proof, the Laplace transform method. Basically, same thing we had been doing in chapter 2. So entire chapter 2, 2 weeks of lessons, simplified into a single viewing window. Okay, all right, we established nearly all the theory part. Let's go to a bit of a technical detail and then we are going to be done. Okay, first, let's establish the linearity property of L. The operator L is linear. What do you mean by that? It preserves the linear combination. What is so-called a linear combination? Does everybody recall? Something like this is called linear combination. y1 is a function, y2 is a function, and c1 and c2 are numbers. So number times y1 plus coefficient times y2, that kind of thing is called a linear combination. And then we take the operator L. What do you get? C1 is a coefficient. L of y1, that's a function. And then c2 is a coefficient. L of y2, that's a function. So what do you get? We have coefficient times function plus coefficient times function. So we have the same structure as before, the linear combination. So operator L is linear. What do you mean by linear? That means it preserves a linear combination, and that's something you'll have to prove. The proof is actually simple because the derivative operator satisfies all this. Remember, it does not matter whether you take the derivative before the addition or after, or before multiplying by coefficient or after. Or equivalently speaking, before taking a linear combination or after. So that's basically it. So we take the linear combination before the derivative, and then take the linear combination after the derivative. You see, that's for the nth derivative. And this one, before the derivative, we take the linear combination. This one is after. That's a property of the derivative. And then we can rearrange them. And then this is y1 part, and that's y2 part. Then what we have what we want, the right hand side. C times L1 of y1 plus C2 times L of y2. That completes the proof. How about the next? The solution of the homogeneous equation is a linear space or a vector space. What do you mean by linear space, vector space? I'm not going to go too deeply into that. That is, it is closed under linear combination. That's what it is, at least in this case. So the solution set, that is, y1 is a solution, which means L of y1 is 0, and y2 is a solution, L of y2 is 0. Then the linear combination, c1y1 plus c2y2, should also be a solution, which means L of that is equal to 0. How do you prove it? Really, really simple, because you just established this one. So L of c1y1 plus c2y2 is equal to, by this linearity property, separate them, and this is 0, and that's also 0. So we have 0 plus 0 equal to 0, and that's what we want. This is a solution because L of that is equal to 0. So much for 2.1, and let's go to the next topic, linear independence. A set of functions y1, y2, y3, and so on is said to be linear independent if the linear combination c1, y1, c2, y2, plus and so on is identically 0, not just 0 sometimes, but not always, but always 0, identically 0, then all the coefficients are 0. Linearly dependent means the other way around. Not all of them 0, there may be some non-zero, maybe 1, maybe 2, maybe all of them. It doesn't matter, at least one non-zero. Then, still, the linear combination is identically 0. In that case, we call it linearly dependent. It's either one or the other. And here are a couple of examples. As a matter of fact, we went through this example before, so let's go through it very, very quickly. And here's an example of linearly independent family. How can you tell? Set up this linear combination equal to 0 identically, which means 0 for all t, and then plug in some t values. I can plug in some other t values, but here I decided to put in 0, 1, negative 1, 2, and we have a system of linear equations. Solve it, all the c's are 0. It's easy to see. How about the next example? That's different. If we have 1, 1, and negative 1, then we have identically 0. So it falls into linearly dependent category there. One final topic which is not very useful for us is a special case of the linear independence or dependence. A pair of functions y1 and y2 are linear dependent if they are collinear. But that's used for the second order only. If you have higher order, then you have to consider 3 functions or more, so it's not really useful. For chapter 6, it was not very much here, so I de-emphasize it great.